lecture today will be about the design factor for load pavement. So, what are the design factors for road pavement? The first aspect or the first parameter we have today is traffic, and then we have the subgrade strength or stiffness. The two will be uh, focused on the course. And we have also water and temperature, like warm asphalt and wet subgrades. And there is another parameter which is pavement material performance. So let's focus now on the traffic. The first information or the first note we need to know in the traffic that the vehicles are classified to some classes, as you can see here in this photo. As you can see here, this photo. The traffic on any road like contain different various types of car, so that's why we need some classification for the cars or the vehicles load depending on their size and their weight. So the first class is class one, the short vehicle. Second class or class two is short vehicle towing, and class three is two axle truck. So this axle and this axle. Class four, three axle truck. So one, two at the back. Class five, four axle truck. So we have one first, one in the middle, and two at the back. And we have three axle articulated vehicle class six. So we have three axle, and we have some heavy vehicles, some heavier vehicles classes. So class 7 is 4 axle articulated vehicle. Class 8, 5 axle articulated vehicle. Class 9, 6 axle articulated vehicle. And class 10, B double. And class 11, we have double road train. And class 12, we have triple road train. So each vehicle or each class of these classes has different number of axle and different number of tires and also different weight per each tire. Okay, so these are the types, and to design the route or the pavement we need to have some estimating of the numbers of the axles or the traffic numbers passing through over the route or over the pavement. So we have a method called equivalent standard axle approach, which is the simplest approach we have to determine the or estimate the number or the traffic passed on the route. So we have ESA, equivalent standard axle. Okay. The design traffic in ESAs is the number of application of a standard axle to cause the same damage to the pavement as the actual traffic over the life of the pavement. So we have a standard axle. We have a standard axle load, and this method will calculate the estimated number of application of standard axle that cause the damage of the actual traffic. So this idea, this method, like sorry, converting the actual traffic to standard or equivalent standard axle load. Okay, equivalent standard axle load because we know the damage due to one standard axle load. So the idea is to convert the actual load to some equivalent axial load, and then using the damage of one axial load, we can estimate the equivalent damage, the equivalent standard axial load damage. So this is the idea behind this method. And we calculate the damaging effect of the actual traffic, load and frequency over the life of the pavement as a single number. So this will be a single number. So we know how much is the damage caused by the traffic expected on this route. Right? Okay, thank you. There is some problems happened to the slide. So now again, the traffic load or the traffic count is estimating by a method called equivalent standard axle approach, ESA approach. Okay, which is the simplest way to do this. The idea behind this method is to estimate the design traffic in ESAs, which is the number of application of a standard axle load to cause the same damage to the pavement as the actual traffic over the life of the pavement. So the idea is we have actual traffic. This method will convert the actual traffic to equivalent standard axle load, ESA, and we know the expected damage the expected damage due to one ESA. So using this method, you will be able to estimate the damage of the actual traffic over the years or over the design life of the project of the pavement. Okay, all the damaging effect of the actual traffic, the load and frequency of the load over the lifetime of the pavement is specified as a single number. So the damage of the actual traffic will be estimated using this method as one single number. And here, let's talk about the equivalent standard axle, ESA. So we have reference loads, for example, single axle carrying 80 kilonewton or 8 ton on dual tires on each side of the axle, SADT. Okay. So if we look here, so we have, this is our example we have. It's called single axle dual tire. This one was the example. So this axle can carry 80 kilonewton. So again, each wheel will carry 20 kilonewton. Okay. So here, this wheel is 20, this wheel is 20 kilonewton. Okay. So the contact stress under this wheel here is considered as from 500 to 1000 kPa, because we already know the contact surface area of the tire, so you can easily know this contact stress. And the middle or the average used is 750. So in average, 750 kPa is used for design. So this only just example of the stresses or the damage due to the this reference load, which is single axle dual tires. And here let's have a look on the articulated vehicle. As you can see, this articulated vehicle we have at the front, we have single axle, single tire, SAST. So single axle, single tire. Okay. And here in the middle, we have tandem axle, dual tire, TADT. And at the end, we have triaxial, triaxle dual tires, TRDT. So we here for the articulated, we have SAST and we have TADT, and we have at the end TRDT. So this is our truck. Okay, and we can know how much is the load for this one and this one and this one. So these are some ideas. This was two ideas about the SADT and SAST, TADT and TRDT. And now let's look at the axle groups. So these are the standard axle loads, SA load. So for single axle dual tire SADT, it contain one axle and two tire. This is the first one here. And we have tandem axle dual tire TADT, two axle and two tires, which is this one here. So this is number one. Just missed this one. So this is SADT. This one is single axle, single tire. So this one is single axle, single tire. Okay, and the third here we have trial axle dual tire TRDT, three axle, two tire per each axle. So if we look at the standard this table, the standard axle loads. So for SAST, the standard load is 53 kilonewton. For single axle dual tire SADT, 80 kilonewton. For tandem axle dual tire TADT, 135 kilonewton. For tri-axle dual tire TRDT is 181 kilonewton. So these are the standard loads coming after like surveying and surveys, and some tests. So we can know, or we already know this values. So these values will be used to estimate our ESA for other load. So what about ESA for other load values? For other load values, the H2 USA Association pavement trial showed that the damage is proportional to the axle load to the power 4. So the damage is proportional to the axle load to the power 4. And this is called the forces power law. Okay, so the H2 give us this formula or this rule to allow matching the damage from other axle group types. So if you have a different or other group type, not from the previous one, SAST, SADT, and TADT, and TRDT, you can use this formula. So SESAs for non-standard axle load will be equivalent the non-standard axle load divided by standard axle load to the power 4. So don't forget the power 4. Okay, so again, ESA for non-standard axle equal to non-standard axle load divided by standard axle load to the power 4. For example, what will be the amount of damage in terms of ESA for one bus of the track shown below? If we look at this track, how much the first or the front axle load, 15 kilonewton, how much the rear axle, 75 kilonewton. The first one or the front one is SAST, the back one or the rear one is SADT. So if we apply our formula, ESA for non-standard axle equal to non-standard axle load over standard axle load to the power 4. So for the front, This is how much? 50, the non-standard, over the standard is 35 to the power 4. For the back, ESA equal to 75 over, if we go back to this table, how much single axle dual tire? 80. So it is 80 to the power 4. So this one, the front one will be zero point 0.8 ESA. So for the front tire, front axle, the estimated damage is zero point 0.8 of the standard axle load. At the back, or the rear, sorry, ESA at rear will be 0.77 ESA. So how much ESA for this truck or non-standard truck will be zero point 0.8 plus 0.77, so it will be 1.57 ESA. So the damage of this truck will be 1.57, the estimated damage from a standard axle load. Okay. Do you have any question, Dylan? That's good. So here again is the damage due to the front axle, 50 over 35. And here is the damage due to the rear axle is ADT, 75 over 80. So the estimated damage for the front axle is zero point 0.8. The rear axle is 0.77. So the total for one bus of this truck is zero point 0.8 plus 0.77. So it is 1.57 ESA. And here, another problem to calculate the number of ESA for one bus of each truck shown below. So for example, we have a rigid truck, this one. We have steer, this is a steer. We have single axle, single tire, single axle, so a SAST. And the drive axle is tandem axle, dual tire SADT. The second truck is articulated truck, which has steer. This is steer, single axle, single tire, SAST, and we have drive, tandem axle, dual tire, TADT, and we have trailer, tri-axle, dual tire, TRDT. And this is the loads for this type of trucks. And now we need to find the number of ESA for one bus of this truck. So let's have a look here on this solution. So for the rigid truck, we have steer and drive. Steer is SAST and drive is TADT. The axle load given for this truck is 65 and 175. The standard load is a load, standard axle load is 35 for SAST and 135 for TADT. So how much is the estimated damage? ESA for non-standard. Again, the force is power, so it is non-standard load over SA load to the power 4. So this value is 65 over 53 to the power 4. This one is 175 over 135 to the power 4. So this equal to 2.26, this equal to 2.28. So the total of this vehicle is 2.26 plus 2.82 equal to 5.00. Okay, and for the articulated, so the total damage for this truck is 5.09 ESA. For the articulated truck, we have steer, drive, and trailer. The steer axles are SAST, the drive axle is TADT, the trailer is TRDT. The given axle loads are 75, 170, and 250. The standard axle load from the tables is 53 and 135 for SAST and TADT, and for the trailer it is 181. So similarly, we will have for the standard for the steer axle will be 75 over 53 to the power 4. This one will be 170 over 175 to the power 4, and here 250 over 181 to the power 4, and this is the values. It will be 4.1 for the steer axles and 2.51 for the drive axle and 3.64 for the trailer. So the total will be the summation of these three values, which are 4.01 plus 2.51 plus 3.64 equal to 10 to 10.16. Sorry, 10.16. So the total ESA for both trucks will be 509 plus 1016 equal to 25, 15.25 ESA. So one bus of these two trucks together will be 15.25 ESA. Okay, so this was like some examples about estimating the ESAs for some trucks. And now let's go to the next part, which is estimating the design ESA. We would like to have the full spectrum of load and loading frequency for a route, but it is rarely available because this need a lot of statistics data, which is not available. So that's why we need approximate method to find the estimated design ESA using the traffic load distribution and traffic counts. So we have a simplest route count for heavy vehicles, HV, number of heavy vehicle as a percentage of the average annual daily traffic. So we have like some data. One of them is called AADT, or the annual or average annual daily traffic, which means that they have recorded the daily traffic for 1 year and determine the average rate. Another information is, or another value, which is HV as a percentage, which is the number of heavy vehicle as a percentage of AADT. So these two values will give us some approximate overview on the traffic buses over the designed route or the designed pavement. And there are some surveys to find these values, which are Way in Motion Survey, WIM, which counts the total number of heavy vehicles and the load carried by each axle group, as you can see here. And we have another technique, which is the vehicle classification counter. So this is a software and camera that detect the different type of vehicles, buses through the or over this route. And here we have single tube axle counter. We might have seen this in some routes here in USA to give or to find some estimated number of the traffic buses on some areas, on some on routes in some areas. Okay, and here is some traffic load distribution from a survey. We just need to have a look on this number. We don't need to go in this with this number, but this is how the values of traffic obtained. So using WIM survey or single tube survey and so on. So this survey will give us some axle group loads and how many SAST and SADT and TAST and TADT and TRDT. This is axle group types as we have learned. So they can have idea on how much uh, load or how much number of trucks with specific load passes through this survey or passes during this survey, and then they can give us a value of number of heavy vehicle and estimated standard axle load over HVAG, which is a heavy vehicle average damage, and ESA over HV. So these are important value, and we will see how we use these values in the next slides. But all these values come from some surveys, and the next one again is some other values from obtained from some surveys. And now the important part is how we can use these values, the data obtained from surveys, to estimate the damage or the ESA damage. Okay, to estimate the design traffic or the design traffic expected damage, we will need to calculate a parameter called NDT, which is the total number of heavy vehicle axle group over the design period. So this will be total number of heavy vehicle axle group over the design period. The formula of this parameter NDT is here. So we have 365, which indicate 1 year, AADT, which is average annual daily traffic count, DF, which is the direction factor, proportion of ADT in the design direction. As you know, we have some routes are one way, some routes are two-way. So this will affect the direction factor. HV as a percentage is the heavy vehicle percentage of AADT. NA NHVAG is the average number of axle groups per heavy vehicle. LDF is the lane distribution factor, also depend on this one because some roads has like two lanes in each direction or more than two lanes in each direction. So this is the lane distribution factor. And we have the final parameter of this formula is CGF, which is the cumulative growth factor or the effective design life in years. Because as you know, the population increasing over time. So we need to account for the population rise in the future. So this is our formula and these are our parameters. So to find NDT, you need one AADT, DF, and HV, and NHVAG, and LDF and CGF. So these are six parameters we have in this formula. Okay, so let's start as some example to find each one of them. So for AADT, the average annual daily traffic count, this comes from traffic surveys again, and this can need to be calculated during a sufficient duration. So because you are taking average over time, so you need to do it for a sufficient duration. And this duration needs to be representative time of the year. So you don't select a time where the traffic is very low or very high. So you need to select a time of year which represents most of the year. And here is a short example about how to calculate AADT. So if we have a set of information from a traffic survey, calculate AADT for this route. So the route type is two-lane, two-way route. Survey duration is 15 days. Total traffic count is 5,000 vehicle. Number of HV is 1,500 vehicle. So AADT will be equal to total traffic divided by the survey duration. So it will be 5,000 over 15, which is 333 vehicles per day. So this is AADT. Okay. The direction factor also comes from a survey, depend on how the traffic was counted. So again, for AADT, you are counting the traffic. So depend on you count the traffic in one direction only or in both direction. So DF will be depending on the technique or the method used to find the traffic count when we are doing the survey. So it can be 1 or 0.5. So if the AADT was determined using one direction only, so DF is 1. If AADT was counted using two direction, so how much DF 0.5. Okay, so this is what we have about DF. And the next is percentage of HV or percentage of high heavy vehicle. Again, this comes from the traffic surveys. So for the same example we have for AADT, we have set of information and we need to calculate the percentage of high vehicle, heavy vehicle, sorry. So we have 15 years of the days, 15 days. The total traffic is 500 and the number of heavy vehicle is 1500. Sorry, the total traffic is 5000 and the number of heavy vehicles is 1500. So the percentage of heavy vehicle will be total traffic, sorry, the total, it will be the number of heavy vehicle divided by the total traffic, and we need to multiply by 100 to get it as a percentage. So the percentage of heavy vehicle will be 1500 over 5000 times 100, which give us 30% of heavy vehicle. Okay, so this is the heavy vehicle percentage. And now in HVAG, so the average number of axle group per heavy vehicle. This also comes from a traffic survey. So we need to calculate for this example the number of average number of axle group per heavy vehicle for these four trucks. We have class 7 truck, class 8 truck, class 9 truck, and class 10 truck. And this is given from a survey data. So the survey data give us the number of class 7 vehicle is 100, number of class 8 is 150, number of class 10 is 200, and the duration of the survey is 10 days. So if we look at how we get this one, the number of average heavy vehicle axle group is equal to total number of axle group divided by total number of heavy vehicle. So if we look here, we need to make this table. So we have the classes, we have three. If you go back, so how many classes we have of the vehicles? Three. So we have 100 vehicle of class 7, 150 for class 8, 200 of class 10. So the number of heavy vehicles, the total number is the summation of these three, which is 100 plus 150 plus 200 equal to 450 heavy vehicle. The axle group per vehicle, if we look here at class 7, how many axle group we have? We have SAST, we have here SAST as well, sorry, SADT, because this one is dual tire. So we have SADT, and here we have TA dt. For class 8, so how many axle group we have? 3. Okay, and here we have 1 SAST, here TA dt, here we have TA dt, so we still have 3 axle groups. Here we have at class 10 we have 1 SAST, 2 TA dt, 3 TR dt, 4 TR dt. We have 4 axle group. So the total number of axle group, which is the number of vehicle times the the total number of axle group, the axial group per vehicle standard number. Yes, depending on the vehicle design, but the vehicle design cause the classification of the vehicle. So I think they have like some standard design for the vehicle. So each vehicle design has a class. So where I get this axle group numbers from the photos or the image on top here. So for each class, you will have like a specific number of axle groups. Okay. So this is just depending on the type of the vehicle. But in the exam, you will be given the classification. So, but if you are in real life, so you need to classify first the vehicles you have to class 7 or 8 or 9 or 10, and then you can find the number of axle groups. So now, how to find the total number of axle group? It will be 10 times 3 equal to 300. 150 times 3 will be 450. 200 times 4 will be 800. So the total number of axle group will be 1550. So now again here just try to update this one. The total number of axle group equal to uh, so let's continue the calculation. So finally we found the total number of the axle group as 1550. So now the number of heavy vehicle axle group will be equal to 150 over 450. So the total number would be 3.44. So the number of heavy vehicle axle group is 3.44, and this is the parameter we was looking at. And next would be the lane distribution factor, LDF. So how can we find the lane distribution factor, LDF? So here is the consideration we have to take when we define the lane distribution factor. Firstly, the number of traffic lanes. So for example, if we have this direction of of travel. So we can have, for example, three lanes: left lane, center lane, and right lane. Also, another parameter is the parked vehicles in the left lane and proximity of intersection and the primary and secondary function of the routes. So this table give us some values of the LDF factor depending on the parameters listed earlier, this four parameter. So for rural areas and for urban areas, so this is the number of lanes per direction. So you can have two lanes or three lanes. So the LDF factor for the left lane will be 1 for rural routes and 0.95 for three lane routes. For center lane is not applicable here, and the factor will be 0.65. For the right lane, zero point 0.5 and zero point 0.3 if it is three lanes. For urban roads, for the for two lanes per direction, so we have LDF as 1 and right lane for LDF for right lane is 0.5 and center lane is not applicable. For three lane route, the left lane LDF for the left lane will be 0.65 and for the center lane as well 0.65. For the right lane will be zero point 0.5. So this is the LDF factor. So again, depending on the number of lanes per direction of the route, and the factor will be given depending on the lane and how many lanes per direction and the parked vehicle on the left, proximity or possibility of intersection, and the function of the route. Okay. And finally, the last factor in this formula is CGF, or the cumulative growth factor, which represent the growth in population over design life of project or of the route development. For a reconstruction project based on historical data, so this can give us some hints about the cumulative growth factor. For a greenfield project based on growth experience in similar routes, also considering the effect of future land development. So this parameter should be taken in consideration when we calculate the CGF factor. And in terms of calculation, the effective design life in years or the cumulative growth factor, CGF, is equal to this formula, 1 plus 0.01 R all to the power B minus 1 divided by 0.01 R. So CGF is equal to 1 plus zero point 0.01 R to the power B minus 1 divided by 0.01 R, where R is the annual growth rate and B is the design life or period in years. Okay, so based on these two information, we can find CGF. Okay, so now all the parameter of the formula is ready, and just a short example about calculation of the effective pavement life while the growth rate is 30% and the design life is 20%. From the given statement, the growth rate, which is R, equal to 3%, and the design life B is equal to 20 years. So if we substitute in the formula CGF equal to 1 plus O1 R to the power B minus 1 divided by 0.01 R. So CGF is equal to 1 plus O1 times 3% to the power 20 minus 1 divided by O1 times 3. Just don't forget that R here is percentage. Okay, so 3. Just be careful when substituting in this formula. So the final CGF value will be equal to 26.9 years. So the effective pavement life or the cumulative growth factor will be 26.9 years. This was a short example about how to calculate the CGF factor for graphic design and calculate NDT. And after calculating NDT, the next is calculating the design ESA or DESA from NDT using TLD. Okay, this procedure is only for bituminous pavements only, and the TLD provides information to evaluate the pavement damage caused by each heavy vehicle axle group. Okay. This procedure can use the WIM surveys. In absence of WIM surveys, pre-summative values can be selected. So some assumption can be used if the survey data is not available. Okay, and here given in this note, the design ESA or DESA is equal to NDT calculated earlier from this formula multiplied by ESA divided by HVAG. Okay, so this is the TLD equal to ESA, the estimated standard axle load divided by the heavy vehicle axle group. Okay, this parameter is given in this table for the granular with thin bituminous surface pavement. The damage type is overall damage. The damage index is ESA over HVAG or TLD. This factor can be taken as 0.9 for rural roads or rural pavement roads and 0.7 for urban roads. Okay, so if we just see, can have a look on some example about this one to have a look how to use TLD factor. So the first class activity or the first example is we have a new mine to build in South Australia. The mine will be running two different types of trucks. Both trucks will be running 500 times per day, assuming that the axle groups of all trucks will be carrying 95% of the standard load. Calculate the design ESA for the mine route to be designed. The mine will be operational for 360 days per year for 15 years. So these are the two trucks we have. Okay, so these two trucks will be running 500 times a day, 360 day per year for 15 years. Okay, so if we have a look on how to calculate this example, so we have two trucks, so it's truck type. The axle we have, if we look at the first truck, we have steer, which is single axis, single tire, and we have drive, which is tandem axle, dual tire. The axle load for this tire is 0.95 the standard, so 0.95 the standard load, which is 53 for SAST and 135 for TADT. Okay, then the standard load, SA load, is 35 kilonewton for SAST and 135 for 135 for TADT. So ESA equal to the non-standard load divided by the standard axle load to the power 4, which is called the powers 4, the force power law. Okay, so here the damage will be 0.95 times 53 over 53 to the power 4. So it will give us this value 0.8145, and all of them will be same because this example is a simple one. So all the parameter will be 0.95 because this was given in the problem. Okay, so this is the damage for the first track. So the total damage for this track will be 0.8145 times 2 or plus 0.8145. So the final value is 1.63. And similarly for the second track or track 2, we have steer and drive and trailer. So for steer, the single axis, single tire, drive tandem axle, dual tire, and trailer is tri-axle, dual tire. And all of them are 0.95 from the standard load. The standard load for the first one, single axis, is 53, tandem axis is 135, and tri-axle is 181. So all of them will be same. So the final ESA or total ESA for this track will be the summation of the three values, which is 0.814 plus 0.814 plus 0.8145. So 2.44 is the total ESA for this track. So if you want to calculate the total DSA for this two tracks, so the total DSA will be 15 years, the operational time, times 360 day per year, the operation days, times 500 times per day. Okay, so this is the total operation days or total operation time for these two tracks multiplied by the total ESA for both tracks, which is 163 plus 2.44. So this for track 1 and this for track 2. So the total number, the design DSA will be 10.98 times 10 to the power 6, which equal to 11 million ESA. So the damage of these two trucks for the total operation period of this mine will be almost 11 million ESA. Okay, this is just a simple example about how to calculate the total damage of a truck or two during a period of time. The second example will be a detailed example about how to calculate DSA using the survey data for different types of trucks. So in this example, we are given the route type, which is two-lane, two-way route, the annual average daily traffic count, which is 3,000 vehicles per day. And here, this note is very important. This value is calculated from one way. And the number of heavy vehicle percentage is given as 6.5%. And the number of heavy vehicle per axle group is 2.5. The design life of this route is 20 years. The traffic growth rate is 3% per year. The TLD or ESA per high vehicle axle group is zero point 0.9, which indicates this is a rural route. So this all the data given for us for this example. So let's start solving this problem. So the NDT will be equal to 360 times AADT times the distribution factor DF times the number of the percent of heavy vehicle times N of heavy vehicle number of heavy vehicle axle group times LDF lane distribution factor times CGF cumulative growth factor. So let's start with the cumulative growth factor equal to 1 plus O1R to the power B minus 1 divided by 0.01R. So it was given in this example B equal to 20 years and R equal to 3%. So the CGF will be, we just have done this calculation very soon. So this is how it is. And this was given as 26.9 years. So if we look at the NDT, so we have 365, AADT is 3000. The distribution factor equal to 1 because it was given that the traffic was counted in one-way direction. The percentage of heavy vehicle is given as 6.5%. The number of heavy vehicle axle group was given as 2.5. The LDF was taken as 1 because it is a two-way ruler route. So two-way was given in the hay. Two lane was given here, and ruler was noticed from here. So if we return back to this table here, so for ruler route, two-way, two lanes per each direction. The left lane factor is 1. So we take it as 1. If we go back here, so LDF is 1 and CGF was calculated as 26.9. So the number of design traffic will be 4.78 million. This is the number of design traffic, and the design ESA or GISA is equal to NDT times TDL. So it will be 4.78 times 10 to the power 6 times 0.9 equal to 4.3 million ESA. So this is the design ESA for this route pavement design, traffic design. Okay, this example is straightforward example, so all the parameter was clearly known. AADT, DF, HV, number of heavy vehicle axle group, LDF, and CGF. So we were able to find NDT. Then the second step is to find DESA. Okay, and that's it for the design factor for traffic, and the next topic will be the design factors for subgrade strengths. Okay, thank you.